Hello everyone, welcome back you all in this new video where we are going to see how to design the combined foundation by using this Excel sheet. So first of all, try to understand the problem statement. There is a two column having the cross section as 250 by 250 in mm and 300 by 300 in mm. They are subjected to the intensity of the load as 300 kilonewton and 500 kilonewton respectively. The center to center distance between that two columns are actually 4 meter. The bearing capacity of the soil at the proposed land is 100 kilonewton per meter square. We have to design a combined foundation being width as fixed 1.5 meter. The material that we have to use for the design of this combined foundation is M20 as a grade of concrete and Fe415 as a grade of steel. Now we have to design this combined foundation by using this spreadsheet. So we are going to complete this design in a few important steps. In the first, we will find out the dimensions of your combined foundation as width of the footing, as length of the footing. Thereafter, we will find out the overall depth of your combined foundation. And then we will go for the checks for the one-way shear and two-way shear to make sure that your project depth is safe or not. After all of that, we will find out how much the reinforcement required along the longitudinal direction. Thereafter, we will find out how much the reinforcement required along the transverse direction. After all of these, we have to prepare the final schedule and detail for this combined foundation. For better understanding of everything, you have to watch this video till the end. And if you are interested in the field of structural design and you are new on this channel, so we are continuously uploading this kind of videos. So please subscribe this channel and share this video with all of your friends and press the bell icon to get every notification. Now let's start the design. But before of that, try to understand how to use this spreadsheet. So you have to edit the values in yellow cells only. You don't need to edit anything in your white cells because formula is embedded in that white cells. So it will give you automatically the values. And this cell will suggest what value of that particular parameter you should select. And this green cell will tell you whether that criteria is passing the check or not. Now first of all, we have to put the grades of material. So grades of materials are M20 for the concrete and Fe415 as a steel. Thereafter, the size of your column as look at your problem statement 250 by 250 and 300 by 300. The both of the columns are subjected to as 300 kilonewton and 500 kilonewton respectively. So that I am going to put in our Excel sheet. So left hand side column is 250 by 250 and right hand side column is what? 300 by 300. With this, the left hand side column is subjected to 300 kilonewton intensity of the loading and right side column is subjected to the intensity of 500 kilonewton and SBC of the soil has given as 100 kilonewton per meter square. Now center to center distance between these two columns is 4 meter, so it is going to become 4000 mm. And the self weight of the foundation we are going to consider as 10% of the load coming from both of the column. Now we have to assume the clear cover, so I am going to assume it 50 mm and the diameter of bar I am going to consider as 16 mm. In respect of all this given data, the area of footing required as 8.8 meter square. But we have given the limit for the width of your combined foundation as 1.5 meter. So I am going to put here as 1.5 meter. So here length of the footing required will become 5.87. It is the suggestion given by your Excel sheet. So more than of this suggestion we have to provide, I am going to provide as 6 meter. So finally width of the footing is 1.5 and length of the footing is 6 meter. Now projection of the footing from the center of your C1 column up to its edge, it is going to become 0.5. Here it is given, and projection of your footing up to its edge from the center of C2 column, it is going to become 1.5 meter. And in respect of all this, we are getting the net upward soil pressure as 88.89 kilonewton per meter square. Now after getting of net upward soil pressure, sheet is going to consider a design step which is passes through the center of C1 and C2 along the length of your combined foundation. And sheet will calculate the shear force and bending moment at different points along this design strip. So it will calculate the shear force at the edge of the footing, then it will calculate the shear force and bending moment under the column C1. Also it is going to be calculated under the column C2 and then it is going to be calculated at the edge of this footing. Now that all calculation you will get here. So these are the shear force calculated at all that different points. How much the shear force you are getting, you will get from here. Thereafter, the respective bending moments at all that different points, here it is given. So at the edge of the footing, we are getting the bending moment at 0. Under the column C1, how much the bending moment we are getting as 16.67 in kilonewton meter, and in between of this C1 and C2 we are getting the zero shear force point, and wherever you are getting the zero shear force point, at that respective point you will get the maximum bending moment. That here it is what calculated by the sheet. The point of zero shear force, it is at a distance of x from the left hand side of your column, from the center of C1 column. The point of zero shear force is what? 1.75. So at this 1.75, maximum bending moment you are getting as 187.5 kilonewton meter, and this is what the hogging moment, because the minus sign is there. And thereafter under the column C2 you are getting the maximum bending moment as 150 kilonewton meter, and here at the edge of your combined foundation you are getting the bending moment as 0. So at both edge of the footing you will get the bending moment as 0. Okay, so in respect of the calculation of your shear force, in respect of the calculation of the bending moment along the span of your combined foundation, the shear force diagram here it is present, and the bending moment diagram here it is present. So at the edge 0 bending moment, under the column 16.67 bending moment, in between of C1 and C2 maximum bending moment is there as negative 187.5, and under the column C2 bending moment is what? 150 kilonewton meter, and at the edge the bending moment is what? 0. So in respect of all this bending moment, we have to find out the how much the effective depth and overall depth is required. So but all these bending moments we don't need to consider, only we have to consider the maximum of all these values. So you don't need to consider the positive and negative, you only have to focus on the numbers. So maximum number we are getting as 187.5 kilonewton meter. So in respect of this requirement 187, it is the service bending moment. I am going to multiply this value by 1.5. So ultimate or factored bending moment I am getting as 281.25 kilonewton meter. So in respect of this ultimate bending moment, how much the effective depth is required? So 260.64 mm effective depth required. So sheet will automatically calculate all these things, and it will suggest that how much the effective depth of your combined foundation should be. So 260. But here I am going to provide as overall depth as 450. If I am considering 260, so there may possibly that on later stage it is going to be fail under the punching and one-way shear check. That's why I am going to consider the overall depth as 450. Now available effective depth is going to become 392. Actually available effective depth is what? 392 mm, and required effective depth was 260, and we are going to provide as effective depth as 392. So we are on safe side, no problem. Now self weight of the footing, here we have assumed the self weight of the foundation. Here this 10% what we have assumed, we have not calculated actually the self weight of your combined foundation, because to calculate the actual self weight of your combined foundation we need to have the length of the footing, we need to have the width of the footing, then we have to depth of the footing. But at the early stage we don't know what is the size of the combined foundation. But yeah, after deciding the length and width of the foundation and overall depth of the foundation, actually we have to consider the at least 12.66 percentage of self weight of the footing, but we have considered what? 10. So that is what? Wrong. So I am going to correct it. So at least I am going to consider it as 12.66. So I am going to consider it overall as 15% to be on safer side. So when you consider the 15%, so a length requirement is going to be what? Increase. 6.13 it is going to become. So I am going to provide it as 6.5 for length of the combined foundation I am going to consider. In respect of all the dimensions and values are going to be changed. Now, but effective depth requirement is what? 261. Again we are safe by providing the 450 mm. Now effective depth available is going to become 392. In respect of that, now here self weight of the foundation we have to consider at least 13.71, but we have considered as 15. So we are on safe side. Thereafter
we have to perform the punching shear check. So sheet will do that, and it is giving that nominal shear is less than of your critical shear, hence our punching check is safe. Means project depth is safe in punching shear.
After performing the punching shear check, the sheet will calculate the longitudinal reinforcement required along the length of the footing at its top face and at its bottom face. So here first of all, how much the minimum reinforcement required as per your IS 456-2000 as 0.12% of width of the footing and overall depth. In respect of this recommendation, there is what demand of the reinforcement as 810 mm square. So wherever there is no requirement to provide the reinforcement, there at least we have to provide as 810 mm square. And the maximum bending moment ultimate we are getting 210.94 kilonewton meter as a hogging bending moment, as we have seen earlier in the bending moment diagram between the C1 and C2 column. The maximum bending moment we are getting as negative bending moment, and that's why we need to provide the reinforcement at the top. Wherever you are getting the negative bending moment or hogging bending moment, reinforcement is needed to provide that at its top. And under the column C1 and C2, you are getting the moment as positive as sagging bending moment. That's why design tensile reinforcement is needed to provide at the bottom face for the both column as C1 and C2. So here sheet is going to calculate the reinforcement required in respect of these bending moments. So at the top face, the reinforcement, design reinforcement along the longitudinal direction along the span of the footing as 1579.14 mm square. If I would like to provide a 16 mm diameter of bar, here drop down list of all the diameter of bars are available. As per your choice, you can select any of the particular diameter of bar. So if I am going to provide 16 mm diameter of bar, so spacing required as 190.99. So this is the maximum limit. You are not allowed to go beyond of this spacing. Okay, so here I am going to provide as 175 center to center spacing between the longitudinal bars at the top face. But if I am going to provide 175 mm spacing, what problem I need to face? Try to understand. Here the reinforcement will be from the center to center, and the spacing I am going to provide as 175. But what about for this projected part? For this projected part, we have to provide the minimum reinforcement. So if the minimum reinforcement I am going to provide, the spacing I am going to provide here as twice of this 175 spacing. So 175 multiplied by 2, it is going to become 350 mm. And as per the coder recommendation, you are not allowed to provide the spacing more than of 300 mm. That's why what we have the maximum limit to provide the spacing as 300. That's why what I am going to keep it as 150 instead of 175. I am going to provide as 150. So longitudinal reinforcement at the top face, this is what the layout for the top face reinforcement for the longitudinal reinforcement. So main reinforcement here required between C1 and C2. So spacing, this is what 150 mm center to center. That is what the safe as per the design requirement. Now for this projected portion, I am going to keep these two bars I only continue, and these bars as an extra as curtail. So for the middle portion, reinforcement will be more, and for this projected part at the top face, reinforcement will be less. Okay, so here spacing is going to become what 300, that is what twice of this 150. Here 16 mm diameter of bar at a spacing of 150 mm center to center, and for this projected part 16 mm diameter of bar at a spacing of 300 mm center to center. So this is about the top face longitudinal or main reinforcement along the span of the footing. Thereafter at the bottom face under the column C1, so sagging moment is there 51.92, which is very less, and in respect of this moment design reinforcement is 371.93 mm square and minimum reinforcement 810. So your sheet will compare these two and will consider the maximum amongst of these two value. If I am going to provide a 16 mm diameter of bar, so with 16 mm diameter of bar spacing required as 372.34 in mm, but again it is 372. You are not allowed to provide more than of 300. That's why I am going to provide maximum as of 300 mm. Thereafter come to this C2. If 16 mm diameter of bar, if I am going to provide 139.4 mm spacing is required. So I am going to provide here as 125 spacing. But again
Here the same problem you need to face at the bottom face. Have a look over the layout at the bottom face. So if I am providing here under the column C2 with the spacing of 125, here I need to provide the 300. So there is no match between 125 and 300. How you will provide your reinforcement? There will be the what complication in providing the reinforcement. That's why I am going to take here as twice of this 125, so that will become 250. That's why under the column C1 I am going to limit the spacing to 250 only. So it is 125 twice of this 250. So what I will do here, one bar will be present here as continue, next bar as a curtail, then next bar will be as continue, then next bar as curtail, then next bar as continue. So here spacing is going to become 125, and here it is going to become spacing as twice of this 125 as 250 mm center to center. So in this way we have to provide the longitudinal reinforcement at the top and bottom, and you don't need to do, your sheet will take care about all those things. Thereafter we have to perform the one-way shear check. So here no shear reinforcement is necessary under the column C1, no shear reinforcement required under the column C2. It is okay. Now just come down and we have to find out the transverse reinforcement. Till now we have calculated the longitudinal reinforcement or the reinforcement along the span of the footing. Now we have to find out the how much the reinforcement required along the transverse direction, or we can say along the width of the footing. So here transverse reinforcement sheet will calculate everything. Here under the column C1, 427.73 mm square area of reinforcement required over 1 meter strip, design strip. So if I am going to provide 12 mm diameter of bar, so spacing it is asking to provide as 209 maximum. You are allowed to provide the spacing less than of this. So I am going to provide as 200 mm center to center spacing under the column C1 in transverse direction at the bottom. So here I am going to provide spacing between these two bars under the column C1 as 12 mm diameter of bar at a spacing of 200 mm center to center. For under the column C2 with a 12 mm diameter of bar, it is asking to provide as what 178. So I am going to provide here as what 150 mm center to center for the bottom. So how you need to provide the reinforcement at the bottom face for the transverse reinforcement? Here it will be for suppose your column is present here. So at a distance of like 0.5 meter from the face of your column and till the edge of combined foundation, this for this portion the spacing of the transverse reinforcement will be what, this much, 150 mm center to center under the column C2. For rest of all the portion, the spacing of the transverse reinforcement is going to become what, 200 mm center to center. If you would like to keep the spacing of the transverse reinforcement overall throughout the span of this footing, so you can keep this spacing as same as 150, that is your choice. But what I am going to do, under the column C1 and up to the edge, I am going to provide here as what, 200, and for here at a distance of 0.5 meter, I am going to provide the spacing as 150 mm center to center. Thereafter transverse reinforcement at the top face, I am going to provide as 12 mm diameter of bar. If you want to change the diameter, you can do that. So with 12 mm diameter of bar, I am going to provide the spacing as 200 mm center to center. So overall provided percentage of reinforcement 0.13, 0.17, 0.13, everywhere we are going to provide the reinforcement more than of the minimum one as 0.12%. So in this way you have to complete the design by using this spreadsheet. Any type of combined foundation you can design by using this spreadsheet. Now after the complete design, your sheet will give you the detailing for your combined foundation in respect of the design result that you are getting from your spreadsheet. So here the sectional elevation that is showing about the reinforcement, there is the top face of the reinforcement placements, and there is the bottom face in respect of reinforcement positioning. Okay, so either you can refer the detail given by your spreadsheet or this Excel sheet, otherwise you can prepare the detail in CAD as per your requirement. So here the sectional elevation, that is what showing the details of your reinforcement. So at the top, longitudinal reinforcement in between the C1 and C2 design requirement is there, that is what 16 mm diameter of bar at a spacing of 150 mm center to center, and for extended portion it is 16 mm diameter of bar at a spacing of 300 mm center to center. Likewise, at the bottom face, the longitudinal reinforcement is actually 16 mm diameter of bar at a spacing of 125 mm center to center, and here at the bottom face for this extended portion 16 mm diameter of bar at a spacing of 250 mm center to center. So in plan also you can see for the longitudinal reinforcement, here it is what the plan of the top face reinforcement. So in between of C1 and C2, 16 at 150 mm center to center, and this is what 16 at 300 mm center to center. These two are same. Likewise at the bottom face, here 16 mm diameter of bar at 125 mm center to center under the column C2, and here for rest of the portion it is 16 mm diameter of bar at a spacing of 250 mm center to center. And then there will be transverse reinforcement. These blue dots and blue circles are showing what? Transverse reinforcement. So at the top face, the transverse reinforcement will be 12 mm diameter of bar at a spacing of 200 mm center to center, and at the bottom face under the column C2 from the edge to the at a distance of 0.5 meter from the face of your column C2, the transverse reinforcement will be 12 mm diameter of bar at a spacing of 150 mm center to center. And for rest of the portion, the transverse reinforcement will be 12 mm diameter of bar at a spacing of 200 mm center to center. That is what also here it is shown in the plan view. For the bottom face, transverse reinforcement under the column C2 will be 12 mm diameter of bar at a spacing of 150 mm center to center. For rest of the portion, it is 12 mm diameter of bar at a spacing of 200 mm center to center. So this is all detail is prepared based on the design result given by your this spreadsheet. So by using this spreadsheet, you can design any type of combined foundation. Thank you very much you all for watching this video.